All right, we're going to be looking at 6A notes today. This is an introduction to a t-distribution, sometimes called a student t-distribution. So we're looking at your chapter 23 inference about means. So when small samples are drawn from a normal population, but we don't know the population standard deviation, a normal curve cannot be used to analyze the sample means. We have a t-distribution is used. The shape of a t-distribution is related to a sample size n. The value n minus 1 is referred to as the degrees of freedom of the distribution. Now the following are the properties of a t-distribution. The t-distribution is a theoretical probability distribution. It is symmetric, bell-shaped, and similar to the standard normal curve. It differs from the standard normal curve, however, in that it has an additional parameter called degrees of freedom, which is n minus 1, which changes its shape. All right, so the symbol for degrees of freedom is this df, and right now it's equal to n minus 1. A t-curve has more spread than a z-curve. As the degrees of freedom increases, the spread decreases. And as the degrees of freedom increases, a t-curve approaches a z-curve. All right, so if we say if our degrees of freedom are greater than 120, we're going to use our z-star values. So this is just a relationship between a t-curve and a standard normal curve. So the curve in black here, that's our standard normal curve. All right, so as the sample size gets smaller, there's more spread. So the red curve corresponds to a sample size of 4, degrees of freedom of 3. And the blue curve is sample size of 7, degrees of freedom of 6. So we're going to look at an example. Here's just that explains what the degrees of freedom mean. You can read it on page 536. This is kind of a summary. You don't need to write this down, but just in case you're interested. All right, let's look at an example here. All right, we're going to be finding the probability under a curve for our t-curves. And you're going to need to have your calculators. All right, so we're going to draw a simple random sample of size n from a population that has a normal distribution with mean mu and standard deviation sigma. All right, so we're going to make a one sample t statistic. So it looks very close to our z-score, with only one slight difference in the fact that here we have t. You can label your degrees of freedom as your sub. Your degrees of freedom is n minus 1. The curve shape of the curve depends on that degrees of freedom. So it's x bar minus our mean over our sample standard deviation divided by the square root of n. And because we're basing this on a sample value, that's why we call it standard error. All right, so we use a t-distribution with means when we don't know the population standard deviation. All right, here's an example question. The temperature x of warm water springs in a basin is reported to have a mean of 39 degrees Celsius. That's our population value. That's what we're told to be true. A sample of n equals 16 springs from the west end of the basin produced a sample mean of 41.5 degrees Celsius with a standard deviation of 4.5 degrees Celsius. What is the probability that the mean is 41.5 degrees or higher? Okay, so since we're given S, we know we're going to be using a t-distribution. All right, we're asked to find that the mean is greater than 41.5 degrees. All right, so we're going to have to find our test statistic. So we're going to find the probability that t is greater than. All right, find our test statistics because we're going to set up our curve. We believe it's centered at 39 degrees, and we got to find the standard error. All right, so our mean was 41.5 degrees minus 39 over our 4.5 divided by the square root of 16. And because our n is equal to 16, our degrees of freedom are 15. All right, so We're going to enter that, compute that test statistic, and you should be getting 2.22. All right, so let's correspond that to our curve. So 2.22, so we're here, 41.5. We're looking for that area. All right, so here we're going to have a different place to look this up now because this is a T-curve. We're going to be not looking at normal CDF anymore. We're going to be looking at T-CDF. All right, so let's go to our calculator. We're in distributions, second distribution, and we want number 6, T-CDF, and look at the parameters that it needs. All right, so it says lower bound, so that's here's going to be our test statistics at 2.22. Upper bound is some big number. All right, now notice we don't have mean and standard deviation anymore. The shape of this depends on the degrees of freedom, which in this case is 15. And then paste it. All right, we're looking up the area under that curve. All right, so that's about, what, 0.021. That's this area. All right, so now let's write our statement. So we're going to have 2.1% of the time we would expect that the mean temperature is 41.5 degrees or higher. All right, so let's review real quick what are the important parts of a t-distribution question. All right, we know to use a t-distribution when we know S. That's telling us to use a t-distribution, and we have a mean. Mean, and we're given the sample standard deviation. To find the probability, we have to change it into a test statistic, or t, with our degrees of freedom. All right. We have to do the math, so we have to find our test statistic. So that's number 1. All right, we're going to do the calculations. That's point number 2. We're going to draw a curve. That's point number 3. We're going to find the actual area. That's point number 4. And then point number 5 is going to be write the statement. So when you complete 6A, you're looking for these, you set up these 5 things.